So now it's time to talk about Niagara, which we can use to create particle and effect systems that simulate and react dynamically inside of our scenes. It's a really powerful tool set, but at first it is important to know that Niagara is not so beginner friendly. It's a little bit unintuitive, but I think over the next 10 minutes I've laid out a framework which makes this as simple as it possibly can be, and we'll start to apply the knowledge of how to make Niagara particle systems to create two of our own right away. So here I am in our Niagara test level where we have 5 different starter Niagara systems, which will cover a lot of the typical effects systems that you'd have to create for visual effects, like bursting impacts like these sparks, ground dust emitters, falling leaves, which are a great way to add life and movement to environments. Then we have our summoning portal where we'll go over how to create some magic effects and some abstract particle effects and how to be creative with Niagara. And then I'll break down this dynamic tracer fire system where we're shooting out these tracers and the particles react to how they collide with our environment, whether that's close by or anywhere throughout our scene. And in the end, we'll understand how to easily use this game dev tool in our visual effects and our films. And we'll wrap up this whole lesson by how to use this and add it into Sequencer so that you get the same exact simulation playing back every single time you render. So we're going to start by looking at these two systems, our ground dust and our spark impacts. So you can select any of these Niagara systems and double click on this blue icon here. If you're using Unreal 5.1 or earlier, Niagara used to have a red color, but now in 5.2 it's this cyan. But inside reacts exactly the same. And let's start to break down what we're seeing inside of our Niagara graph. So Niagara is made up of emitters and particles. So the icon that you're seeing in the middle is our emitter. It's the thing that's spawning our particles. So in our Niagara graph, each orange column is our emitter, and inside of that emitter, we can adjust how the particles should behave. But with these sparks you're seeing in the middle, the emitter is the source, and the particles are the sparks themselves that are being shot out of the emitter. Now these graphs execute from the top down, so they start at the top with our properties and go through each one of these sections and each individual module. And then we modify our data, we modify our emitters or the behavior of our particles through these different modules. And you create the modules by hitting these plus icons next to each of these sections. And these modules are simple node graphs, just like inside blueprints, where we're just sending and receiving data. So if we look at our orange emitter on the right, we have 4 different sections that we have to worry about, which are the different stages of our emitter and our particles. So the first section is the emitter update, where we're going to decide if we want to spawn particles in a burst, like our sparks, or if we're going to make a continuous flow, like our ground dust. Next up, in particle spawn, we're actually going to set the properties and initialize the different settings of our particle upon spawning. Below that, we have particle update, where we'll adjust the behavior of our particle over time with different physics forces. And lastly, we have our render section where we'll decide if we want to render out a sprite, a mesh, light, or a couple different options we have for how we want to render each particle. But first, let's take a closer look at the emitter update. So the important thing to know with the emitter update is, do we want to spawn a burst like the spark impact or a flow like our ground dust? So typically you'll either make a module for a spawn burst or a spawn rate. And the other module that you should know is the emitter state. And this is going to give us the life cycle of our emitter as a whole. And by life cycle, you can think about how often we're going to loop this emitter. So the ground dust, we're going to loop that infinitely, and it's just going to keep going on forever. Whereas a spark burst, we're probably just going to want to burst that one single time. And at the bottom, you can see all the different spawning modules we have available, like spawn burst instantaneously, spawn per frame, or spawn rate. So next up we have our particle spawn, and the name of this section is probably the most confusing because in our emitter update is where we're actually creating the particles for the first time, but particle spawn is where we're setting the initial properties of each particle. So with this initialized particle module you're seeing at the top, we'll set really common attributes like the lifetime, where we can set a range between a min and a max lifetime like you're seeing here. And we can also set the color, size, and rotation. We can also create a module for the location of where we want to spawn our particles. Do we want to spawn them in a grid or use a shape location where we can select different primitives like a plane or a box or a cone, anything like that, and we can spawn our particles inside or on the surface of these primitive shapes? And lastly, we have velocity and forces where we can add a starting velocity or different physics to help randomize these particles as they're spawned. And we can add velocity in a constant linear way or in a cone where we're giving it a specific direction that we're pointing in. So let's look at how we'd apply these to our spark impact and ground dust. For the lifetime, you can see the lifetime of these sparks are going to be a lot shorter than the ground dust where it's lingering around. The size is obviously very different where we have these pretty large smoke puffs for the ground dust where these spark impacts are really small and they move very quickly. And lastly, we have color where we can set that yellow hue that you'd have in your sparks as opposed to more of a gray brown that you'd associate with ground dust. But we'll discuss later on how we can actually evolve and change the color and size over time in the next section. Next, for location, spark impacts are obviously coming from a really small point source, whereas ground dust, we're spawning from a larger box and spawning particles inside of it. And then we're giving an initial velocity to this spark impact, whereas we're just letting the ground dust simulate. It doesn't have an initial velocity that we're giving it. So that's particle spawn. The next section is particle update, where we can change the behavior of our particles with physics forces. So it's important to know here, each of these modules is executing every single frame. So when you set a value for something like wind force or curl noise force, just know that whatever value you're entering there is being applied every single frame. So we can use modules like scale color and scale size to adjust how these properties evolve over time. And when we're entering in values to any of these modules, we have the same data types we had before, like you can see vector and float here, vector for the RGB and float for the brightness or the alpha channel of our scale color. But we also have curve data types where we can change that value over time. And each of these data types is created by hitting this down arrow that you're seeing on the right. And you can search for vectors, floats, and curves in different data types, as well as different math operations like multiply, add, and divide to quickly find what data types you'd like to enter in each of these sections. And then we have a lot of different modules for creating physics forces and applying them to our particles. So this is the list of all the forces we have access to. So we have things like gravity, wind, curl noise, which can use some really extreme values, but can add a lot of nice randomness, especially to magic effects. And then we also have point attraction and vortex forces. And if you use these forces, you'll need to add a solve forces and velocity module at the bottom of the particle update section. But Niagara will also notify you to do this as soon as you add any of these into your particle update section. So some of the modules used for this spark impact are things like gravity, wind to give it a little bit of turbulence, curl noise, and collision. Now, collision is really interesting because you can change the direction of your emitter and how it affects the world, like we have with this dynamic tracer fire set up here. And then the particles can collide with anything that's visible in the scene. So instead of hand animating all of these different interactions, you can just let this more complex simulation play out and calculate all the physics on the fly. And lastly, we have our particle render settings, which just decides what actor type we're going to display our particles as. So the most common one is probably the sprite renderer. And when you select sprite render, it's going to create a plane for each particle, and it'll just display a texture or a material on that plane. But we can have 3D objects with our mesh renderer. We can also render out lights or decals, which are new in Unreal 5.2. And you don't have to just choose one renderer. You can select multiple. And it's very common to select a sprite renderer and a light renderer, and you'll see that in a lot of the examples I have coming up next. So that's our Niagara graph and how our emitters are going to execute. We start with the emitter update, which is, do we need a burst or a continuous flow of particles? Then we have particle spawn, where we're going to initialize the properties of our particles upon spawning. Then we're going to update our particles and adjust their behavior over time. And finally, we're going to render them out and select how we want to display our particles. So now let's hop into our scene and create some Niagara particle systems and take a look at some of the different examples. So here we have our spark impacts, and I think as a first lesson, these would be a great Niagara system to create from scratch. So let's hide these in the scene and let's create this together. So I'm going to create a new Niagara system. And when you click that, you'll get 4 different options here. And typically you're going to want to select the first, where we'll make a new system from selected emitters. And selected might as well mean template emitters. So we have a couple basic templates which are useful, and a lot of our particle systems can be started from one of these presets. So we have a fountain, hanging particles, which are kind of like dust swirling through the air. We have an omnidirectional burst, and then we also have blowing particles, a confetti burst. But let's start from this directional burst. So I'm going to click on this, press this green plus button, and select finish. And now it's going to add that emitter into our Niagara system. And we'll call this NS Sparks 02. So let's take this and drag it into our scene. And you can see it had that first initial burst, and now we're not getting any more particles. So in our emitter update setting, let's click on this emitter state module, where we can control the life cycle. And you can see in this case, our loop behavior is set to only play once. So we want to change this to infinite, at least while we're creating this, because we want it to constantly loop so we can evaluate the behavior of this Niagara system. So emitter update is telling us how we want to spawn these particles. So we've created spawn burst instantaneous. And I think 75 is a good particle count to start with. So we've decided we want to burst. Now let's go to particle spawn and start to initialize some of these particle settings. So there's a lot of different knobs and settings that we can adjust here, so it can be a little overwhelming, but it's actually pretty simple as long as you look at the header of each section. So under lifetime mode, we have 2 options here, which are direct set and random. Random just gives us a range between these 2 numbers, and it randomly picks a value between these 2 upon spawning. So if I set the lifetime minimum to 0 and I set my lifetime max to 0.2, we can see that this reduces the time quite a bit. But if I set this to something like 0.5, each particle dies out at a different time. Whereas if I change this to directly set it to 0.5, all of the particles die out at the same exact time. But let me change this back, and I'll set the lifetime min to 0.2 and our lifetime max to 1. Next, we can change our color. So we'll just tint this over to a nice orangey yellow color. Now, if I look at these sparks closely, I'd say they're a little bit thick. So we could thin that out with our sprite attributes and change the sprite size. So here we have a random range. And the difference here between uniform and non-uniform is it will give us an X and a Y value if it's non-uniform, whereas a uniform just gives us one global value. So in this case, a uniform value will make our sprites turn into these circle shapes, whereas a random non-uniform is going to let us squish these circles so they start to resemble the shape of sparks. But let's reduce our sprite size minimum to something like 0.5 and the X of our sprite size max to something like 1. And now that we're setting our initial properties of our particles, you can also see that we have an add velocity in cone node here, which we can change how we want to add our velocity, but in a cone gives us a directional burst like we're seeing here. And we can adjust things like the cone angle and make them very direct, and a really small cone angle or something really wide where it gives us a lot more randomness. In any one of these pieces of data, we can click this down arrow and we can turn this float value, which I can tell just by hovering over the section, and type in range, and then we get a random range float option show up at the top here. And now instead of having one value, we can pick that randomized range, and I can change this to something like 90, and now each particle is going to randomly be assigned a value between 0 and 90 upon spawning. And if we wanted to get rid of this random range value and turn it back into a float, I would just hit this reset button and I'll get back to our original float value. You can see this is already set up for our velocity speed, where they've set a random range between 250 and 750. So that's it for our particle spawn. Now we have particle update, where we change the behavior of our particles over time by applying physics forces. So just to see what this does, let's disable every single one of these and see what would happen if we remove all of our particle update modules. And I'm only going to enable solve forces and velocity so that our velocity is calculated from earlier. And you can see here, it's a very different look. They're almost like they're floating in space because we don't have gravity, we don't have drag or wind or anything like that. And that's why it's important to set these up. So let's enable gravity force. And by default here, if you want real world gravity, you want to set this to negative 980 centimeters. And this will match the real world scale of gravity. The next module here is drag, which is going to add resistance in the air And this is a great node to use if you're ever using a physics force and it's starting to make your particle system go berserk and your particles fly in all these different directions. Drag can help to reduce those extreme values and smooth out the behavior of your physics, but typically it's also going to slow down your simulation. So you're going to lose some speed when you enable drag. And then the last two affect our color and the sprite size. So this scale color is doing something interesting here, where it's actually making our particles darker towards the end of their lifespan. So let's delete this and let's create a scale color from scratch to show how we can do this, because this is something you'll use all the time inside Niagara. So in this case, we want to swap out our scale alpha settings for a curve. So if I click on this down arrow and I just type in curve, you can see that we can create a float value from a curve. And the result it gives us off the bat is really similar to what we had earlier. But we can highlight over our keyframes inside this template, and we can press the 1 key to turn them into smooth Bezier curves instead of linear keyframes. You can also change this by right-clicking your keyframes and setting them here. And there's also some really nice presets, which are some common things that you'd select, like fading in or out with these Bezier keyframes, or having it start at 0, scale to 1 halfway through its lifespan, and then go back to 0 by the time it ends. In our case, we want this graph to start at a value of 1. So in this graph, 0 to 1 is our time in the x-axis, and the y-axis is what value is actually going to show up in this scale curve. So at 0 seconds, we're going to have a value of 1, and when our time is set to 1, we're going to have a value of 0. And the reason that we're between 0 and 1 here is because our curve index is set to normalized age. So it's going to normalize the lifetime of our particle and set it to a value between 0 and 1, which makes it really easy to use these curve graphs. And this reference will be created by default anytime you create any curve data. And lastly, we have scale sprite size by speed, so we can increase the size of each of these particles the faster it moves, which can help us cheat the idea of motion blur. This isn't 100% accurate, but it is very close to resembling what motion blur would look like, because motion blur on particles can get pretty tricky, because the way a video game engine calculates motion blur is not like we're calculating motion blur with path traced renders. We're using a lot of motion vectors and approximation so that we can run motion blur in real time, which is why it's really important to look at reference footage of what you're trying to create, so that if you ever do something like this where we're kind of cheating how it's going to appear in the game engine, we're doing it because that's what it really looks like in reality. And the last thing we can add is a collision node. And now if I expand the lifetime in our initialized particle, I'll set this to 2, we can see these start to bounce around inside of our scene. And there's a couple settings we can adjust here. Like advanced aging rate, we can make it so it will start to age a lot faster once a particle has collided. So if I set this to something like 20, they would die out really, really quickly once they bounce. And we can also change how bouncy these are by adjusting our restitution to something a lot lower. But hopefully that shows you the building blocks of a particle system like this. And I think you'd be surprised by how often these modules are used in all different sorts of particle simulations, because a lot of these things, especially when we're emulating things that happen in real life and we're not creating magic particle effects, if you were making falling dust or debris, a lot of them are going to use a very similar setup to this. Now, 2 things I want to cover really quick. One thing you might notice is that we do get these trails from some of our particles. There's just this little bit of noise that's left around after our particles are run, especially for these really bright particles that move really quickly. And this is because of our anti-aliasing settings inside of our scene. Now, in previous versions of Unreal, you could adjust your anti-aliasing settings inside of your post-process volume, but in Unreal 5.2, they've removed these and hidden it a little bit. Now, because there's so many different settings that are built into Unreal, the developers have hidden some of them so that you're not bogged down by a gigantic list of settings. There's already a ton of settings in all of these different menus, and sometimes the only way to change these internal settings is by entering in console commands. So one of those settings is r.anti-aliasing method, and any console command you enter in here, you can put a space question mark at the end of it and press enter. And now if we check our output log, we can find out what the setting is inside of our scene, and it'll give us an answer here. So we can see that our anti-aliasing method is set to 4. And if we look above here, that means 4 is temporal super resolution. So temporal super resolution is something new in Unreal 5. It does a good job of getting a lot of detail out of your geometry, but this method is calculated over time, which is why it's called temporal super resolution. But if we set this to an older method like temporal anti-aliasing, this will actually remove some of those artifacts that we get from this new anti-aliasing setting. And if we ever want to render with these settings, we can go into Movie Render Queue and make a new config and change our anti-aliasing settings here by overriding our anti-aliasing and selecting temporal anti-aliasing, or by creating a console variable, pressing this plus icon next to console variables and typing an r.anti-aliasing method and setting that to 2. And both of these will do the same exact thing. Now, next to our spark impacts, we also have these ground dusts set up, and these ground dusts are emitting a constant flow of particles, and this can be really useful to have effects like this in your scene that never run out, like an infinite fog machine that's going to keep playing back and add interesting movement into your shot. And now let's quickly go step by step and create one completely from scratch, not even using a template in this case. So for now, I'm going to create an empty system, and we'll call this NS Ground Dust 01, and then we'll drag this into our scene. All right, so let's start in our Niagara graph and add an empty emitter. So first it's going to show us the properties here. One thing to always check on, because we're using Unreal for visual effects, is we always want to enable determinism, because this gives us a random seed output, which will allow us to get the same results when resimulating these Niagara systems. A lot of people have the impression that because Unreal is a game engine and we get new simulations every time, that this is just the way it is, but we can work around this by enabling determinism in our emitter as a whole and in the system itself by clicking on the blue box here and enabling determinism. All right, so we can skip over emitter spawn and go right to emitter update, because emitter update is what's going to create our particles in the first place. So let's create a spawn rate because we want a constant amount of particles. And you can see here, whenever you've created a node and there's a discrepancy or a dependency that's not met, Niagara does a good job of showing you what these issues are and giving you these simple buttons to fix your issues. So we really need an emitter state module in this section, or the Niagara system won't be able to compile or calculate. So let's fix that. And we have our two essential modules, which are the emitter state and some version of a spawned node. So by default, when it's set to system, this is going to grab our lifecycle settings from the system itself. So instead of grabbing those settings from the emitter state, it's going to grab it from the system state here. And in this case, we'll have this loop indefinitely, so it never stops. And when we have that, the loop duration doesn't matter quite as much because we don't have a burst that would be happening every 5 frames here. So we'll just leave it to 5 by default. And let's set our spawn rate to 50. I'm not exactly sure what that spawn rate should be, but I think 50 will give us a good start. And let's add in a sprite renderer at the bottom so we can start to see our particles in 3D. So right now we're just spawning a ton of particles on top of each other here. So now let's give these particles some initial attributes. So under particle spawn, I'm going to make an initialize particle node. Here let's set our lifetime to something like 3 seconds long. We can keep our color to white for now. And then let's change our sprite size mode to random uniform, and now our particle size will be randomly selected between 5 and 10. So these are our initial settings. Now let's set the location of where our particles are going to spawn, and let's create a shape location. In this way, we can select a primitive like a box or a plane. And now you can see where this box exists in 3D space based on where these particles are spawning. And from here, we could adjust the size of the box and change it in X or change it in Y, depending on what we want. And we also have a setting here for surface only band thickness. So if I keep this disabled, we'll just spawn the particles inside of this box. But if I start to enable these settings, you can see that the box itself is now hollow and all of the particles are being spawned outside of that box. So in our case, we want them to spawn inside, and we'll make this a 500 by 500 grid. So one problem in our system here is our lifetime is set to 3, but if you look in the scene, our particles are never dying out. They're just existing once they're spawned. So one thing we'll have to do under particle update is create a particle state node. And all that this does is it has this tick box which says kill particles when lifetime has elapsed. And now we have the correct behavior of our particles. But we do have a problem here. These don't really resemble smoke plumes whatsoever. And one of the biggest lessons you should know early on about Niagara is it's not just about the behavior of the particle, it's also about the materials you use for your particles. So right now we have the sprite renderer, which gives us this default sprite material, which to be honest is pretty boring and just doesn't give us the look of smoke. So let's create a basic smoke material that we can use for our particles. So I'm going to create a new master material and we'll call this smoke particle. And now I want to create a smoke material that animates over time, kind of like our torches did in our cave scene. So how can we do that? As a quick reminder, we can create sub-UV animation, and we get a couple options here. We have texture sample, parameter, sub-UV, but we also have this particle sub-UV option. So let's create a particle sub-UV and see what that is. And you'll see that it looks exactly like our texture sample, except this node, because it has particle in the name, is able to talk to the particle settings inside of Niagara. So we can grab one of the default textures here. If you type in sub-UV, you can see that Unreal starts with this T_smoke sub-UV, which is an 8x8 sprite sheet, and it has this smoke that evolves over time. And the reason we're not just using the regular sub-UV animation is that this doesn't actually loop once this animation is completed. You can see at the bottom right that this looks different than our smoke texture on the top left. So we need our particles to play through this sprite sheet over its lifetime, where it starts with this first image at the start of its life and it ends on our 64th image by the end of its life. So let's set up our material. We have our particle sub-UV, but one thing we have to do to the material itself, if I select the brown box here, we still want this to be a surface. We still want it to be the default lit shading model, but we want our blend mode to go from opaque to translucent because we want our smoke to be semi-transparent. So what we can do here is we can plug in this alpha into the opacity mask. And one thing we can do now that we have these particle nodes is I can right click in our material graph. Let's scroll down to particle. And now all of these settings are different data that can be passed between our material graph and our Niagara graph. So the most common used of all of this list is definitely going to be particle color. So by using this particle color, we can use the same information that's being entered in from our initialized particle settings. So it'll grab the same exact RGB and A data and pass that into our material. So right now, I'm just going to take the RGB of our particle color and plug that into the base color. And then let's take the alpha of our particle and multiply that by the alpha of our texture. And then I'm going to browse to this material and let's assign this in our sprite material right away. And if we look up close, we can see that they are this little 8x8 grid, so we still need to add in that sub-UV animation. But if I change our particle color in the initialize particle module to something like 20, you can see that we immediately can change the color of our particles like this, and you can see that at least that part is set up correctly, and our Niagara graph is talking to our material graph. So to set up the sub-UVs, we need to update our particle over time and change what is being shown by the particle. So underneath particle update, we can type in sub-UV animation. And if we look at the default settings here, our sub-UV animation mode is set to linear. Our start and end frame is between 0 and 63, which is correct because we have an 8x8 grid. But we do need to assign our sprite renderer here. So let's just assign the sprite render, which we have below. And everything is correct now inside this sub-UV animation setup. But there's one thing we have to do inside of our sprite renderer, which is scroll down to our sub-UV settings and change our sub-image size to an 8x8 grid. And now if we look at our particles up close, you can see they're correctly animating over time, but they just pop in and out, and they're all facing the same way. Their rotation is exactly the same. And now that we see these in the scene, it's easy to say that they're way, way too small. They're still looking like these tiny little dots. So let's go back to the top. We'll go to our initialized particle, and we can make the sprite size a lot bigger. So our minimum sprite size we can set to 30, and I'll set the maximum to 100. So they're just way, way bigger in our scene. If we click on sprite at the top here, we can also add in a rotation. So let's set a random rotation. So now each particle will randomly rotate between 0 and 360 degrees. Another thing we can do for our shape location is let's squish down our box size and set Z to something like 1. So all of the particles are spawning on a flat plane as opposed to spawning inside of a tall box. Now, one thing I keep seeing is this harsh line, and that's happening because our particles are intersecting with the floor. So one thing that's really nice to do for smoke particles, if we go back to our material, we can add in a depth fade and plug that into our opacity. and this will just smooth out the intersections of our particles. And now you can see we're starting to get somewhere. We do have our smoke reacting in a way, it's animating, but we don't have a lot of movement within the particles themselves. The particles are still just spawning in place and they're popping in and out. So to fix that popping, one thing we can do is go to particle update and let's create a scale color. And now we can adjust the RGB and alpha of our particle, which will be fed directly into our material. So now let's create a curve for the alpha of our particle that fades in and out. So if we go to our scale alpha, we can type in curve and we can create a new float from a curve. And now we have this new timeline. So if we want this to be really smooth as it fades in and out, we can select this little ramp up, ramp down at the very end here. And now we get a really smooth curve. Another option we can do is this pulse out, and we'll just drag this pulse a little bit in between just so the particles stay visible for longer. That's great. And one thing to know, this scale curve is a way that we can multiply this entire graph by another float value. So if I wanted to multiply this by 5, it would make our alpha a lot thicker, but alphas are going to clamp at 1 no matter what. So it only gets so thick, and this can start to break it pretty quickly. But this can be really nice if you need to affect the brightness of your sparks. You can multiply them by something like 10 and make them way brighter, but it's not really going to help us with smoke, so I'll set that back to 1. And the last thing we should do is just add a little bit of behavior and movement by adding in some physics forces. So we can add one to our particle spawn to give us a little bit of velocity right away when the particles are spawned. But you can see we get a couple errors from this red bar at the top. And all we need to do is press this fix issue button, and that'll create the solve forces and velocity at the bottom. And now you can see that we have this rising steam, which is not really what I was going for. So let's set the Z back to 0, and let's add in between 10 and 20 in X, and we'll just get a little bit of wind direction by doing that. And we could even add in a range here, even though it's a vector, and we could set the minimum, we'll keep that at 0, and let's set our maximum in X to something like 50. And then we can start to see how that velocity affects our smoke system overall to give us a bit more randomness. It's a little bit fast, so I'll probably just set that down to 25 to start. And lastly, let's just add in a curl noise and give us a little bit of turbulence. So curl noise is great just to add some randomness. If you set this to something like 50, you can start to get some really extreme values where most of the system is looking good, but a couple straggling particles will go pretty crazy outside of your scene. So it's good to pair this up with a drag module, and this will just start to dampen some of the velocity and start to get rid of some of the extreme values that can happen with some of these simulation forces. But even now, this is looking pretty intense for our turbulence, so I'll probably set that curl noise strength down to something like 20. But definitely play around with these. The particle behavior can change drastically depending on what you're trying to create, and the noise strength and noise frequency dramatically change their effects and the way they make your particles move. So definitely experiment with every particle system you make. And now we have a pretty robust ground dust setup that fills an entire area. One last thing that I didn't cover before, if we go to the top for our properties here, we talked about determinism, but one checkbox here is called local space. Right now, if I drag our emitter up and down, you can see that our particles end up being created into the world depending on where that emitter starts from. But if I change this over to local space, you'll see that all of the particles in the world are now parented to our emitter, and now we can move our entire system as one complete actor. So for stock elements like sparks or dust or anything like this, I typically like to set them to local space so I can move them around and rotate them depending on how I need them to react in the scene. But it is worth knowing that different systems like this dynamic tracer fire will only work if they're not in local space and they're actually bouncing off of different things inside of the world. So it's definitely not for every particle system, but where it makes sense, I definitely try to enable local space and parent the particles to the emitter. But now it's your turn. Hopefully going through creating those two examples helped you understand a little bit more in depth on how the Niagara system works and the type of modules you should be adding into each of those sections to create your Niagara system. So with that new knowledge, go ahead and create a rain system on your own. I don't want to give you any specific briefs on how to do this, but it would be great if you could find some live action footage and start to create a rain system comparing 1-to-1 all of the different attributes, the color of the rain, the speed, and the gravity. If you can add water impacts on the ground and maybe even add decal wet marks on their impacts. We haven't gone over all the techniques to do this, but I think the best way to learn is by doing and solving problems as you go. So give it a shot, see how far you can take that, and then we'll pick it back up in the next lesson and teach you a little bit more about user parameters and how we can customize each of these Niagara systems so we can make creative changes on the fly. All right, so now we're going to create a couple more Niagara systems, but I want to talk about Niagara user parameters and how we can use those to create controls for our particle systems that we can adjust on the fly, just like in material instances. So we had parameters inside of our material instances. We can create parameters for our Niagara systems. So we can do this on the left side of our menu. There's a user parameters tab, and if you press the gray plus icon, we can create any type of data that we'd like. Usually it's going to be a float or a vector, but we have this whole list of drop downs that we can choose from. And we can also create a user parameter by pressing that down arrow next to any data set. And if you click on read or make a new user parameter, it'll autofill based on whatever data type was already there. So let's go ahead and do this for our ground dust. So I'm just going to select our Niagara system and let's open it up. And that user parameter tab is right here. It's a little hard to see just because there's so many windows open at the same time in Niagara, but we'll press on that plus icon. But let's make a new float data. And just for this example, let's call this alpha and let's set it to 1 by default. And now if we go over to our scale color module, we can just take our user parameter and drag this over to the scale curve. And you can see now it links that up with our user parameter. And now if we change out this alpha to something like 0.1, our smoke will become a lot more transparent, or we can set it to something really high and it'll become thick. So I'll set this back to 1 by default, but the real power of having these parameters is not to have them inside of our Niagara system, but it's so that they're exposed when we select our ground dust in the outliner. So here I can set this to 5 and change this dynamically inside of the scene. And where this becomes really useful is when you have two different Niagara systems next to each other, and you can give the same system different parameters so they'll have different behavior, but you don't have to make a separate Niagara system every single time. So on the left, we have a Niagara system where the alpha is set to 1, and on the right side, the alpha is set to 5. So if I want to create a parameter for our RGB controls, I would just click this down arrow and type in parameter. And now you can see we can read from a new user parameter. Now this will create this scale RGB parameter on screen left. And now I can just right click this and rename this to color. And now when I save that, we can see we have this parameter that populates in our details panel. And we can do the same thing we were doing before, where we can change our color here to something really red or really blue. And now you can do this for any data or any slot that's inside of the Niagara graph. So you could make a turbulence control under your curl noise force, you could set up a velocity control, or you could set up a size and lifetime control. So as a last example here, let's create a new float variable, and we'll call this size. And we have this random uniform range for our sprite size at the moment. But let's say we just wanted to input one value, our maximum value, and automatically calculate that minimum size. So we don't have two different variables to mess around with. So I'll set my size to 100 by default, and I'll click and drag the size over and set our maximum value to 100. But for our minimum, one thing we can do is we can click the down arrow and let's type in multiply. And we can multiply a float by another float. And now it'll create two new variables that would be multiplied together. So now if I drag the size in to the B input, I could set A to 0.3. And this way we'd get the same exact result that we had before. But now when I'm in the 3D world, I only have to worry about adjusting one parameter here, like setting this to 200, and it'll calculate that dynamically on the fly. And now that we've set everything up in the right way, you can see when we drag a point light into our grid of particles here, you can see that it starts to react just like smoke would, and we can get some nice detail and fall off between our layers, even if we stick a point light in the middle of our smoke sim. And this is the way I prefer to deal with smoke and naturalistic effects, is not by bringing in really dense VDBs into Unreal, but it's by using the systems inside of Unreal to their fullest, embracing the fact that we're in a game engine, and using the tools of a game engine to mimic the things that you'd see in real life, like ground dust or different effects like spark hits, or our next simulation that we'll talk about, which are these falling leaves. So these falling leaves are a really nice touch, especially for different environments that you might want to create. It's a great way to add movement with these tumbling leaves and particles without having to animate anything by hand. So for your assignment, I want you to create some falling debris like you can see from this clip in Indiana Jones. Just smoke particles coming down. Try to add clumps of dirt and different user parameters to control the amount of dust particles, the amount of leaves that you might have, and the amount of dirt clumps. Try to find something that's pretty interesting and create a system that is falling smoke, debris, and leaves all combined together and controllable with user parameters. Try to find one single clip that you can try to match to exactly when you're first setting up your particle system, and keep going until that system gets as close as possible. Try to make it match one-to-one with your reference footage before moving on and see exactly what it takes to get it there. And then take that particle system and bring it back into our tunnel environment and see how it looks when combined with the rest of your scene. And now let's take a look at some advanced techniques inside of Niagara by taking a look at our last two examples. So I think the two other use cases that you should look at using Niagara for are, one, to create dynamic particle effects and just create new looks and effects that would only work with particles and combining them in interesting ways. And the other is to create interactive systems where you control one or two things and then a series of chain reactions goes off. That's all handled by Niagara, so you don't have to animate every single thing by hand. So first, let's talk about this tracer fire and how we're able to combine several different Niagara emitters together inside the same Niagara system to create these chain of events. So the way this is set up is we have our tracer fires, which have a lot of velocity coming out from our muzzle flash. Those are propelled forward, and then when they collide with our environment, we're generating a collision event. And this collision event can be used to drive new particle systems and then spawn particles from that location. So we can create events in three ways: from collision events, death events, or location events. So in order to generate this collision event, our overall emitter here has to be set to a CPU sim target, and this requires persistent IDs. This just creates an ID for each particle that spawns, and then based off of that ID, we can say, hey, particle 2071 collided here. Now let's generate a new system based off of that collision. So we're generating that collision event here, and then in our spark impact emitter, we have this event handler, which is what's spawning our impacts. So in order to get this event handler section to show up, you just have to click on the add stage button and create a new event handler, and then assign your source to whatever location or collision events are happening inside of the scene. You want to change your execution mode to spawned particles, and then enter a spawn number for the amount of particles you'd like to spawn from this event. And by using these event handlers, we can cause these chain reactions across several emitters, and this opens up a lot of possibilities. If we go over to our summoning portal, we can also spawn particles from other particles in a different way. So let's open this system up, and let's go to the bottom, and I'm just going to enable these two fire swirls. So the way this is set up is we have one lead particle at the front of each one of these lengths. So in order to spawn this trail of particles behind an existing particle, we just need these two nodes. And the first one under emitter update is spawn particles from other emitter. And here we can select which emitter we'd like to spawn our particles from, in which case we have fire swirls 001. And then we can set our spawn rate. And when you create this node, it'll also create a sample particles from other emitter node, which will set the position of this particle spawn when we initialize our particle settings. And then once these particles are spawned, we still have our forces underneath, like curl noise, wind force, and our other physics forces, which adjust the behavior and movement of this trail of particles. But the initial position is based on following that original fire swirl particle. So I won't break down every single thing from this summoning circle, but I've created this template just so you can start to see how you can start adding in different amounts of complexity to your Niagara systems. And all of these fire particles are actually using the same exact flipbook that we're using for the torch in our cave scene. And then to spice this up just a bit, I've also created these two decals on the floor, which use our color grade material function from earlier. And I'm also taking a simple noise texture and panning that through and multiplying it by our texture. And I've also added in this custom rotator so that we have a little bit of extra rotation going on with this decal in the center. But all of this is just driven by the material itself, and there's no part of this summoning portal that's keyframed whatsoever. And one last technique I wanted to share are dynamic material parameters. So this is just one more way for you to pass data from Niagara into your materials. So right now we have this pink layer of rays which are rotating around and evolving. So I'm using this dynamic material parameter to drive some of the settings inside this material. So I have things like speed, tiling, and this flare mix decides the amount of detail that we're getting from this ray material. So if I open this up, all I have here is I have a dynamic parameter node inside of my material graph. And you can make this by just typing in dynamic parameter. And if this material is used inside of a Niagara system, it should automatically populate the names of these indexes here. And as you can see, I'm taking things like this speed float variable, and I'm just doing some simple math. So with this speed variable, I'm multiplying it by this time input and plugging that into a panner node. So I'm adjusting the speed of this panning node and using that to drive the speed of this animation. But importantly, what I'm doing here that takes this one step further is I'm taking the user parameter that I have for speed and dragging that into the speed parameter of this dynamic material. And by doing this, if I minimize our Niagara system here, now I can adjust the speed from the details of this Niagara system. So if I set this to something crazy like 5, just so we can start to see the difference, you can see that has a direct effect on our pink rays going on there. And by increasing the tiling here, I've now increased the tiling of the God rays material. So by using dynamic material parameters, we can send data from Niagara all the way into our materials and use user parameters along the way to control that from our outliner. And it allows for per particle material changes. And again, if we had 3 or 4 of these Niagara systems in our scene, we could have all 4 of them have unique custom parameters and adjust everything inside the details panel. And again, because all of these are parameters, just like we could do with our materials, we could add a Niagara component into our sequencer and then add in a track for any of our user parameters. So we could actually animate our color, our flare mix, our size and speed, and change that over time, all within sequencer. So I hope this starts to show how you can start combining these different systems together and why it has taken a little bit of time to learn all of these individual pieces. But once you understand the workflows and how that data is sent between all of these different editors, we are finally tapping into what makes Unreal pretty special. And hopefully now you can see the workflow for adjusting all of these different inputs, parameters, and pieces of data on the fly within our scene. And just so you're aware, all of these different modules, you can double click on any single one of these and open them up and see exactly what's going on underneath the hood. And you can see we're doing the same principles that we had with our blueprints, where we're getting data from somewhere, doing some simple math in between, and setting the different parameters. Now you can open up any module to see how it's created, and if you want to make your own, you can just press this plus icon, and now type in Scratch module, and now this will create a brand new module where you can add in your different types of data, and then set that data afterwards. And you can also create your own module by right-clicking in your content browser and going to Effects, Script, and if you select Niagara Module Script and use the NMS prefix, this will also create a module, but this way you can use this module in any Niagara system you create inside of your project. So for your last assignment here, I think now you've learned everything you need to know to start creating fireworks and chain together these multiple different events and emitters together and try to add some user parameters so you can change things like speed, particle count, and color to get practice customizing your Niagara systems inside your scene. Now there's many different ways to do this, but try to do this on your own by thinking through the problem and using the frameworks you've been taught so far. Try not to use another outside tutorial to do this at first, but afterwards, that's a great way to check your work and see how you've done it and how other people can approach the same problems inside of Unreal. But the main thing to learn here is that creative and technical problem solving that you'll have to do with Niagara. So do your best to create this entirely on your own. So if you want some additional ideas for some assignments just to get some more practice using Niagara, I made this short list of a couple different project ideas you could try. The first would be create your own summoning portal. Try a different color scheme, a different theme. Mine was kind of based around fire, but if you used nature or wind or water, think of the different ways that could affect that. Or just using a completely different type, like some purple magic, whatever that means to you. Try it out, see what sorts of behavior you can give your particles, and just try to be creative and come up with something new. And from there, you could try footstep dust, explosions, and try to create some new flipbooks and sprite sub-UVs to create explosions of your own. You could also try to create some magic spells, Harry Potter style, or different portals, as well as some laser beams, or different nebulas, star fields, or different space effects by using some really dense particle clouds and try to manipulate those in different ways. So now let's talk about using Niagara inside of Sequencer. And Niagara is actually extremely straightforward to use inside of Sequencer as long as you know exactly where to look. And there's only two things you need to know to get started. So the first thing you should do is enable the Niagara Sim Caching plugin. This is a new feature in Unreal, so don't worry if you don't have this. Like I said, there's two ways to approach this workflow, but this is the most accurate tool to cache your simulations. But all you have to do is add your Niagara actor into your sequence like we've done with this blowing particles system. And we can create a track for a sim cache, which is what this plugin is. And all you have to do is press record and it'll run through your entire timeline between your in and out points, which are the green and red markers in your timeline. If you do this, you should be good to go. And our other option is the system life cycle. Here we can set the in and out points of a simulation inside of Sequencer. This can even be used to set up the timing of different spark hits or different particle sims that are going to burst on cue. And the only thing you have to do is right click this life cycle track and then go to the properties and go all the way down to the bottom of that list, down to the age update mode, and pick desired age. And this will allow you to scrub through your timeline with the Niagara system. So let's see what this looks like in a real project. So here's a system where we have some particle systems that are looping throughout the scene, but we also have many particle systems that are frozen in air, like these different spark impacts. And in this example, you can see that we can drag our timeline and you can see all of the particles as they go through. And we can also reverse our camera at the same time. Now, the more you reverse it, it can get a little bit buggy, and that's just the way it's going to be with the system life cycle if you're using the older versions of Unreal. But we can still see exactly where to expect all of these particles to land. And as long as you have the same render settings, all of your renders should match each other. It just may look slightly different inside of Unreal. And now if I select this muzzle flash and we see this tracer come down, you can see that the way that this is set up is by having this system life cycle here. But let's delete this and make this from scratch. So now this muzzle tracer is just firing constantly and it's not moving to the speed of our timeline. So if we wanted to add this back into our sequencer timeline, all we have to do is add a new track and at the top select Niagara System Life Cycle Track. Now when you create this, it'll come in where your current time indicator is. It's always good to turn your snapping on as you drag this around so it snaps onto whole keyframes. And then right click this life cycle track, go to properties, and change your age update mode to desired age. And this is the one key setting that will start to cache your Niagara sim in any version of Unreal, and this will lock your simulations to the timeline. But our other option is adding a track for a Niagara cache if you're using the latest version of Unreal. Now just go to the first frame of your sequence and press this little record button, and Niagara will go ahead and cache this Niagara track. And now you'll have the same exact simulation every single time. So if I wanted to add a spark impact when he slices through with his lightsaber here, I have these two particle systems that are lined up in the scene, but they're still looping. So let me add both of these into our sequencer. Let's add a Niagara component and add our system life cycle. Let's right click that, go to properties and age update mode to desired age. And now this is also useful because we can just use this to set up the timing of our Niagara system. So we can see here, oh, the sparks start a little bit too late, so I can slide those forward to frame 74 here, or even one earlier, and set up specific timing for your Niagara systems. And then once you have that timing, you can still go back and add a Niagara cache, and then it'll cache with your updated timing. Now, as long as you go through your projects and do that for every single Niagara system that you need inside of your scene, you'll get the same result every time you render. So one thing you can do to organize those is to create a new track and then add a new folder. And we can call this Niagara. And then in the search box, we can type in Niagara and then select everything inside of our scene and then drag this into the Niagara folder. And that way you can click on this down arrow and now it hides it from everything else in your scene in case you just want to worry about the characters, or you can pop it open when you want to update your Niagara systems. And that's the entire workflow, so it's pretty simple, but can be used in really interesting ways. Now, if you're following along, you can take the dust and debris elements that you created earlier and add those into our tunnel environment and set up your Niagara particle systems in this way. And it's really, really important to make sure you are simulating your game whenever possible to really know exactly what's going on inside of your scene. As you can see here, we didn't add all of these background actors into our simulation. I had some levels hidden from our simulation, but now they're all appearing at the same time. And you can see every single layer is set up this way using the system lifecycle. And if you ever need to, you can also drag this forward before your timeline even starts if you want to offset your simulation. But definitely make sure to be simulating your game to know exactly what you're going to receive out of movie render queue. So one thing we haven't talked about yet is using physics inside of Sequencer. Now there are a couple different ways to do this depending on your final render settings, but I'm going to use this project here, this lightsaber battle. This is a free download on unrealforvfx.com if you want to open this up and see how this works, because this is just taken from the original project file. But I wanted to walk through how the physics are set up because Niagara is still frozen per frame using this setup. We can scrub back and forth, and all of the Niagara systems are set up using the Niagara life cycle. But one thing that we're doing here is animating simulate physics. So if I scroll down in the details panel of this drone here and go to the physics tab, by simply keyframing simulate physics while these drones are being force pulled into the ground, by doing this, we're handing off the animation and we're inheriting the velocity from the animation when we toggle simulate physics here. And what this looks like as the final result, if I simulate this viewport, I can still scrub around here just like I was doing before. But when I play, every single time I play through here, the physics will be different. So if I just keep scrubbing here and pop back, now we have a dynamic physics that will change every time. And that was something I wanted to try out and achieve in this specific example. But what if you wanted to bake out a single physics simulation so that you could scrub through and it would be the same every single time? The easiest way to do that is with Take Recorder, which is a plugin that I believe is enabled by default, but it's just called Take Recorder. And when it's enabled, you'll go to the window, just type in Take Recorder. And we can use this to record the animation of any actor inside of our scene while the game is running, and we can bake it into keyframes. That's the whole purpose of Take Recorder. This can be used for physics simulations, but it can also be used for motion capture and recording it while our game is playing. So when I opened up Take Recorder, it's now created a pending take, which is a new sequence. But if I wanted to open up that previous sequence, Vanguard Clash Final, I would right click on the sequence I want to record inside of and then open this in Take Recorder. And now the way that this works is I'm going to select the actor that I would want to record, and then I would drag this drone from the outliner into this gray box in the Take Recorder window. And when I do this, typically you'll just want to change that record type to possessible if it's just a regular static mesh inside of your outliner. And what it's going to do is it's going to record a keyframe for all of the different properties inside of the details panel here. So we probably just need the transformation. We don't need the spawn track or the visibility track because that's not going to be animated at all. So let's just keep the transform track. And for now, we can uncheck reduce keys. Now all we have to do is start simulating our game. And then I'm going to press record in Take Recorder. And then it's going to play through our sequence and record keyframes on every single frame. Now when it's done, to review what we just recorded, you'll have to go to the top of Take Recorder and press this Review Last Recording button. And from here, we can see that now that we can scrub through the animation of our drone. And now you should have a new subsequence, this track inside of your sequence. And if I look inside of the subsequence, you'll see this is where all that transform data is. In this way, because it's keyframed inside of Sequencer, we know that we can just repeat that recording over and over again and we'll get the same result. And you can see this was created inside of scene 1, take 1. But if I wanted to bring this into our other sequence, our original sequence that we started in, one really great trick is you can actually have two content browsers at the same time. And a great reason for that is we can save two different locations of folders in our project. So I want to save the location of this drone pound sequence. So I'm going to double click in here and browse to this asset. And now we can see, okay, this is in content cinematic takes, today's date, and scene 1. And then in content browser 2, I have our original sequence that we started with. So I'm going to open up our original sequence, and I'm going to make a new track called a subsequence track. And this will just allow us to plop another sequence inside of this sequence, and then we can nest as many as we want together. And now I can just click and drag this from our first content browser into this subsequences track. So what you'd have to do is find this drone inside of sequencer, and we would have to delete this simulate physics keyframe because we don't want to use the physics simulation anymore. We just want to use our keyframes. And now as I scrub through, we have our recorded physics animation. And if we were going to render this out, we could render out AOVs because it would be the same every single time.